Okay, perfect. Thanks. All right. Hi, guys. I'm Christina. I am the London chapter lead for AI Camp, and I'm going to be introducing the speaker today and hosting this session. So today, Zack Akil from Google is going to be talking about end-to-end Google Cloud AutoML vision in virtual reality. So the presentation will demonstrate the AutoML process within a VR environment, thanks to his wonderful GIFs. Hopefully that will be seamless throughout the presentation. And this will be using Google Cloud AutoML vision object detection, TensorFlow Lite models, Unity, and Oculus. And specifically, we'll be looking at how to build ML virtually and how this can be done in a virtual world. So a bit of background on Zack. He's a machine learning engineer and developer advocate at Google, and he specializes in image and video data problems. He spends most of his time building unique and experimental ML applications that help inspire other developers to use ML in new and creative ways. So just a bit of session logistics here. If you're joining for your first session, we have the recordings shared on YouTube, which will be released shortly after the sessions today. And we also have an in-session Q&A. So if you look at the bottom of your Zoom window, you'll be able to see the Q&A tab at the bottom. And this is where you'll post the questions throughout the session, and we'll have some time dedicated to answering those at the end of the session. As well as this, we have our Slack, and I can share the bit.ly invitation there. The channel is AutoML, where we'll be discussing and networking after the sessions. And so if we don't reach your question in time, then we'll be able to answer it during that through the channel throughout the day. As well as this, the announcements will be posted there. And we have a raffle today, which uses the Twitter hashtag. So feel free to reach out to us at AICampAI. And the hashtag is AutoML. So that's it for logistics, and I'll hand over to you, Zack, to start the talk.
All righty, thank you very much, Christina, for the intro. Hello, everyone. Let me share my screen here, and we'll get started. One thing I'd also like to quickly test is, because I like to kind of touch base with the audience from time to time, and I know that Zoom has a raise hand functionality, and I'm wondering if anybody who has the ability to raise their hand, please do so now, so that I can sort of check how many people are ready to interact with that level. I haven't seen, is it, okay, I don't see any raised hands, so I'm assuming that's not enabled, or it is enabled?
Is enabled. I'm not sure you can see, but I can see a lot of people raising hand,
oh, really?
Like more than 50, 60.
Oh, okay.
Yeah.
Okay, so I cannot see that.
Yeah,
so
this one only host can see the, but anyway, yeah.
Okay, that's fine. I might then go use you, Bill, as a conduit to that data. So I won't ask too many questions, but once or twice I might check with you to see how many people raise their hands. So remember that about 50 raised their hands then, and we can use that as the
Okay. Oh, okay. Yeah, go ahead.
Cool. We'll get through this. All right. So yeah. So my name's Zack. I'm a machine learning engineer and developer advocate. A bit about the kind of things I like to build, because that will kind of give you a bit of insight as to what I'm probably going to show along the line. So first thing is, I love everything physical machine learning. I got started programming with Arduinos and Raspberry Pis. So anytime I can bring machine learning into the physical world, I get a huge kick out of that. And some examples of projects that I've done in the past have been things like this, where it was a sort of visual neural network or a physical neural network visualizer. And this is actually visualizing the weights of a scikit-learn model being trained in real time. So you can kind of see the flow of weights with the learning rates and stuff. Virtually useless in terms of how you can apply it, but it's just pretty to look at. Another more recent example is something I built during my last 2 years at Google, and this was a smart bicycle that would use object detection with a sort of rear view of the bicycle. So as you're cycling along, you'll see the different types of traffic that are coming up behind you. And funny enough, this was using a bit of Google technology called the Edge TPUs. And these are like little small, specially designed hardware to run machine learning at really fast sort of inference times. So this was an object detection model running on a Raspberry Pi, and you might be able to make out the millisecond time for inference was about 15 milliseconds. So it's like truly real-time machine learning. So I like those kind of applications. And then something that I built with AutoML early on was a robot here, and I've got it loaded up here. So this was a robot I built. This was using Google Cloud AutoML image classification. And I built this in about a day. And what it was a way to sort of regulate what I was eating at the time. So I would drop a snack on the desk. It would take a photo using the Raspberry Pi, send that up to the trained model in the cloud, and then based on the response, swipe or not swipe the food. And the images it was trained on were literally, I Google searched images for junk food, Google searched images for healthy food, and threw those into AutoML. It spat out the model, and then I sellotaped together a robotic arm. So that's the kind of things I like to build. And today is no different. I'm going to be showing like a pretty quirky example, but one that's a bit more sort of relevant in that, given that I like to build physical demos, and given that we're now moving to a much more virtually distant world, I wanted a way to still be able to build these demos, but not need to actually like collect the physical things. And also when presenting demos, if I'm presenting a physical demo through a webcam, it's not that interesting, but I found ways of presenting demos through virtual reality, which are a lot more interesting. And the great thing about this is I've been used to giving some talks virtually recently, and it's great, but I just miss how much things can go wrong when I'm doing a physical demo. For example, my smart bicycle, one of the times I presented it, it didn't technically catch fire, but it caught up in smoke because I touched some cables together that shouldn't have been touched together. But I miss that, and I feel like building things in virtual reality, there's just so much more that can go wrong. And so that's why I'm very excited to present for the first time this virtual reality demo. Hopefully, like you should see, like there's a huge range of different platforms for building with virtual reality. And the one I'm using today is the Oculus Quest, which is supposed to be like the most popular one at the moment. And yeah, let's get right into it. Also a little sort of preset is that I'm talking a lot about Google Cloud AutoML vision object detection specifically. So I'm just focusing on that one AutoML. However, Google Cloud has all the different other AutoMLs for video, text, tabular data. And at the end of the talk, I'm happy to answer any questions about any of the other AutoML products. But for this one, I'm just talking about object detection. And for object detection, we have a problem. We have this fictional company called Hindcycle, and they are experts in hindsight. And they figured that it's not good to just bury all the rubbish, and it's probably better to dig it all up and recycle it properly. So that's the problem we're going to try to solve today. And the sort of task, as you can imagine, is given a stream of unsorted rubbish. We need to visually inspect it and sort it into the correct category. And let's actually just dive right into the virtual reality. So this is easily the most complicated setup I've ever done for virtual talks. So I hope it works, but you know, I like it when things go wrong. So let's see. I'm gonna click into it, and already I have to, you won't see anything yet because with the new lighting setup, I have to quickly draw where it's safe for me to go. There we go, and continue. Okay, yeah, okay. And then I will boot up. You won't see anything yet. And as it's booting up, tensions are rising. And I'm going to begin the sharing process. And let's hope this works. Okay, so I've proceeded to share it. And I should be able to, if I go to the right, and okay, this Oh. Wait, come back to me. Where am I? Oh yes, we have ourselves a failure. Let's go, let's go. Come back to me. Where's... Okay, so you won't see anything yet. Oh, oh. All right, do we have visuals? Can you see what I see? Bill, I'm gonna need you as I'm wired in.
Yes, I can see the house, the room, the table.
Okay, okay, that's good. Okay, so you need to stay online. You're like that. You're like my connection out of the matrix because I can't see the screen. So you let me know if it goes dark. So we have ourselves our factory, and we have ourselves our stream of trash coming in. And we've got, okay, this is some organic matter, and we have some colored bins here. This needs to go into the green bin. Organic matter goes in there. Oh, this is more organic matter into the green bin. Oh, that's gonna go there. And this is some glass. Oh, that one's went. If they go all the way through the conveyor belt, I get negative points. So this needs to go into the right bin. Okay, positive. Okay, and 0, but more is fallen in. Okay, it's a bit tricky to get everything. Okay, cans. Those are metal. Cans go over there. I'm going to try to move as smoothly as possible because I know the frame rate isn't going to be as good coming through Zoom. And okay, yeah, this is already, okay, my manager's going to kill me. Like I can't move this quickly. Okay, this is going poorly. All right, so I need to scale this. And this is where I want to build a machine learning model to visually inspect these things for me. And to do that, initially, we can kind of think of, we need a camera in here and we need to start taking pictures maybe. So let's bring in a camera. All right, so what we have here is a little virtual camera that's positioned around here, and you can see kind of my hands on the screen. Bill, is that coming through, Bill?
Yes, we can see it. It's
cool.
Great, really impressive.
Cool. So we've got a little virtual camera here that's kind of taking pictures as these things are going past, and we're going to use that as our input data for whatever model we're going to build in our AutoML. So in this virtual reality, so far all we've got is, well, one, we've got a failure to sort trash, but we now have a little virtual camera that is going to take photos for us that we can then label and feed into AutoML. So let's come out of virtual reality and let's get back to how we're going to use these labels.
Wow, that's really impressive.
Oh, that's just the start.
Awesome. Okay.
So let's see how I'm doing for time. I'm doing okay for time. Okay, so we've got these pictures, and what we need to do with these pictures is we need to start thinking about, well, one, we need to save these pictures. So I'm using a game engine called Unity to build this virtual environment. And if you're not familiar with Unity, yeah, it's a game engine. So it's a program used to build games in virtual environments. And it actually has a lot of really good examples of like how to build virtual reality apps. So that's not too tricky. That's not too like obscure of a task. What is obscure of a task is maybe actually given some images of pictures taken within a game engine. How do we extract, say, labels that we can then use to train a model? So let's look about that. So first things first, how do we get the images that we take in a virtual world out of the virtual world and as like JPEGs or PNGs? And that is actually fairly straightforward. So in Unity, it's like 2 lines of code to, given a camera in the virtual environment, convert that to a PNG, and then given a PNG, stream that to a file path. Because it's all in C#. So if you're familiar with C# and .NET, it's all that kind of stuff. So it's pretty straightforward to do, and we're able to get a whole host of images that we could potentially use to train our model. All right, so we've got our images, but these are unlabeled images. And if you've ever built any kind of image model and it's with your own data, labeling images is relatively easy if it's just image classification. Object detection, it's a huge pain. And that's where in the real world, we've got like labeling services. So Google has their own called like data labeling service, and you can just provide your unlabeled images and run out of disk space. And you can provide your unlabeled images a PDF of instructions to label those images, and they'll get people to actually label your images for you. I'm building this in virtual reality. I don't want to bother anyone. I just want to generate labels. So let me show you how I can do that. So first thing first to look at is understanding that game engines are really, really cool in that there's a lot of built-in utilities to look at the camera and do cool things with that. So you can, given a 3D environment, you can drop in a 3D camera and it will allow you to say, okay, given something else in the world, I want you to calculate exactly where that object is relative to what the camera is seeing. And that's really powerful, because if we're able to say, oh, just calculate where the bounding boxes are, generate them, and then use that to train a model, that cuts out the most painful part of building models. And that's exactly what I'm going to show kind of how to do. So first of all, let's imagine we've got our cherry here, and then it's positioned arbitrarily in 3D space. And then built into Unity, and it's built into most other game engines, because it's a very sort of common thing to do, is we can say, given this 3D position, tell us exactly where it is on the screen that the camera has like drawn to. So we've got our 3D object, and then we call world to screen point, pass in the position of our 3D object, and it will tell us the exact in pixels where that object is on the screen. And you could probably already see, like, this is really, really cool for machine learning, because we can just generate bounding boxes and positions of things. And that's exactly what we can do. So how do we use this to generate bounding box? Well, built into Unity as well, there's more functions. So we've got a function that literally is .bounds. And what that will do is that will actually tell us a 3-dimensional bounding cube around every single object. Now, if you combine that 3-dimensional bounding cube with the previous function from the other slide of how to get the 2D equivalent points on the screen, we can just take all the corners of that cube, project them onto the 2D screen, calculate the min and max of each of the X and Y coordinates, and that will give us the bounding box. And voila, in a couple of lines of code, you can have perfectly generated bounding boxes. Although these are not perfect. You can see there's a bit of padding there. And you can see, like, if you've got this 3D bounding box, it's always a cube. So even if you've got an obscure shape, it's always going to try to fit a cube, and a cube won't always fit perfectly to everything. And if you look at a cube from a different angle, it might like skew it a bit. So using this is relatively fine. And by all means, you can use these kind of bounding boxes, which have a bit of padding, throw them into AutoML, and they'll still work. It's just that you won't get consistent padding back if you're not giving it consistent padding. So ideally, you want type bounding box. And it also, if you train a model with the type bounding boxes, there's extra functionality you get. Like, you get to be able to see like the exact size of things. Like you can kind of calculate, okay, what's the size of this object? If we have a type bounding box, we can assume different things. So how do we generate type bounding boxes? This is a method I came up with. And what it is, instead of using that generated 3D bounds from the game engine, which is very efficient, I created this less efficient way, which is actually looking at each individual point of geometry on every 3D object and projecting that to the 2D space, then doing the min and max of that, and that gets us our type bounding box. I have, I'm going to provide a link to the GitHub where I've got like all this code. So if you want to generate your own object detection tools or object detection data sets using tools like Unity, I'll have the code to generate like perfect bounding boxes. And in fact, here is a quick example of this sort of explanation of kind of what I just went over about bounding boxes. So first thing I'm explaining here is there's the 3D location. Hopefully this is readable. The top line here, yeah, this is just the location in the 3D space. And then we have the location in the actual screen space. So you can see as the cherry moves, both things change, but you can see one is changing in 2 dimensions because it's going across the screen. And what's extra cool is if I say, ignore the rest of the side panels, all you need to focus on is just the two screens. If I have a script here to move it, but if I stop that and I actually say, like, move the camera, you'll notice that the 3D position of the cherry won't change. but the 2D camera screen position will, because it's what the camera is seeing. But that's a neat thing. But anyway, let's get the cherry moving again, and then let's get it rotating, and let's look at our bounding boxes. So the initial sort of very efficient bounding box, and this was the code when I searched generate bounding boxes in Unity. This was the code that I kept finding, and it looked like this. So this is what the bounding boxes look like. And you think, well, that's kind of weird, but if I zoom in on this side, you can see how that 3D box that's already there is kind of, it looks weird in different perspectives. But I changed that out for my looking at just the mesh, and we get much tighter bounding boxes. Anyway, I've got the code on the GitHub. That was just something that I put a lot of work into. So no matter what, I was going to mention that in this talk, even though it's very, very niche. So that's me indulging in the really juicy problem that I solved. How to actually take these boxes and generate them into a CSV file. Again, it's all just C# in Unity. So I can, given that generated rectangle, turn that into this line in a CSV file and write it out. And this is what the labels actually look like. And this is the format that the Google Cloud AutoML takes. And if you're interested in more, there's a link and it goes over this format. And I believe this is a standardized format for object detection. So it takes in, first of all, you can tell it exactly if you want this label assigned to the training set or the test set. But for just ease of use, I set them all to unassigned, and AutoML will automatically split your data for you. And then the next part is the name of the image that's stored in Google Storage, and then along with the label and the coordinates of the bounding box within that image. So that's the format of it. And what's great about this, once you get in a script, it will just generate them for you. And then we're on to the training of the model. And I have it over here. So here's actually Google Cloud. And we've got, say, after I've run my image export code to like take pictures and export them from the Unity game engine, I can drag and drop them into Google Cloud Storage, which if you're not familiar with it, it's basically like Google Drive, but for big applications. And you can see here some example images. So if I click here on this one, here's an example image that got uploaded. So I just drag and drop them all in here. I've only got about less than 200 images. And then the CSV file that is also uploaded, I have that here as a CSV file, and it doesn't show me a preview of it, but that's just got the rows of all the different labels that was generated with the bounding box code. And then to train the model, over here, I've already got the data imported, but to import the data, it would be just pointing it to that CSV file. So it'd be in here, browse, go to wherever you've got the CSV file stored, be like there, and I click, oh, that was uploading direct. So select CSV file if you've got the labels, browse, things, and then there, boom. I would select that, hit upload. I've already got them uploaded so we can see what that looks like. And what's great about this is it actually gives you a visualization. So you can make sure that the bounding boxes you generated are in fact where you think they are. And this has saved me multiple times when I've tried to do something like this. And I've looked at the sort of output in AutoML and seen that the bounding boxes are slightly askew. So what's great about this, we can go in, check that they're all there. If they're not correct, I can edit them and update them. So it's a built-in labeling tool. And to train a model, this is where things get pretty cool. I've already trained a model, but I go to train a model and I can train one that's going to be purely hosted in the cloud. And that's going to use a lot of proprietary technology to train like a wide and deep neural network, all that stuff that's going to be huge in terms of like memory consumption. Or I can click Edge Model. And this is where things get super cool. So I'm able to train a model that's going to be downloadable and run in, say, like on-premise applications, or run on the edge, or run on Arduinos or Android phones. And in fact, that's exactly what I did. And one more point to note. This was the initial training data I uploaded. And you might be able to notice something a bit askew with it. And that is that most of the things are pointing in the same direction. And so when I first generated this data, I didn't code up the randomization of objects properly. And so they were all pointing in the same direction. And when I saw this happen, I was like, oh no, the model's going to overfit surely. And I was genuinely like, oh, it's going to overfit. I got to retrain it. But then after I trained the model and deployed it, the model didn't overfit. And you'll see that in the final demo is that AutoML, Google Cloud AutoML, automatically does data augmentation. So it automatically will take a small set of images and rotate them, skew them, and set them. It does all these different techniques so that even with just 100 images, even with overfittable aspects of the image, it will auto-rotate and try to make the most robust model with the images you give it. So that was a really cool feature that I actually kind of proved worked in this demo. Finally, the model deployment that we're going to see soon. When I click that edge, deploy to edge, it's going to train a TensorFlow Lite model. And if you're not familiar with TensorFlow Lite, it's a sort of standardized format for compressed machine learning to be deployed to edge mobile remote devices. And it's especially good if you want them to run super fast, so very low latency applications, and also remote applications. So if you don't have access to internet, or you want to deploy it in maybe like a factory that isn't allowed to connect to the internet for like security reasons, TensorFlow Lite is like a go-to tool for that. And fortunately in Google AutoML, it will allow you to export directly to TensorFlow Lite. Final thing, TensorFlow Lite, it's a standardized format. Obviously it works well with Android. Oculus Quest, the most popular VR headset, happens to pretty much just be an Android phone under the hood. And therefore, my thinking was TensorFlow Lite should work on the Oculus Quest. And TensorFlow Lite in Unity is actually a kind of a relatively common thing, although it's listed here in this really easy to use URL under the experimental folder of the TensorFlow GitHub. But it does work. However, if you're going to embark on trying to deploy TensorFlow inside a Unity game, it suggests that you need to compile your own version of the TensorFlow Lite interpreter. This requires a lot of different tools. This was easily the most complicated bit for me, and it took me a long time to kind of get everything installed. I don't compile things normally. I just run like Python in the cloud most of the time. So this was very difficult for me. So what I did is I actually compiled the version of the TensorFlow Lite interpreter and just put it on my GitHub. So if you're going to go down this route and you want to experiment with deploying TensorFlow Lite in a Unity game for demo purposes or to like proof of concept MVP stuff, I recommend go to this GitHub, and then there's a pre-built version of TensorFlow that you just drag and drop into your project, and it will take care of any missing library errors that you might get. But with that, let's go back into the matrix and deploy our machine learning. So if Bill, you come back on, and then let me know when you're able to see what I see. So I'm going to go.
I see some slides going on. It's some like the desk. Okay, now, okay, I see. I see the room.
You see the room, okay?
Yes.
Okay. You see the room, and we're still going. Okay, we're not doing well in terms of productivity. Let me. Oh wait, I shouldn't rotate around. I should use this. Okay, I'm gonna go over here in the corner of the room. We have a laptop. Right, and I go and I. Okay, so this might be a bit familiar. We have ourselves the AutoML interface. We can see how we can look at the labels. And these look like good labels. These look like good labels. Okay, that's good, okay. And then let's go to train a model. It actually tells us a bit of stats about our data. Like, okay, we've got enough data. Not much, but we have enough. Start training. Make sure we have an edge model. Yes, we definitely want that. And then we can even say like if we want to optimize for low latency or high accuracy. So we'll just do a middle one. And then we choose our amount of training time. 24 hours is the default, but if it converges early, it will stop training and you don't get charged for anything. So a small model like this takes less than 1 or 2 hours. And after it's done, we get our TensorFlow Lite model that we can just download. It's actually about 5 megabytes. So this size of USB stick is completely ridiculous. We'll go over to our thing over here and we will plug it in. All right. Now, anytime an object comes in, this is going to use the TensorFlow Lite model to run on this image. And based on the detection, it will move this grabber to it. And whatever object this grabber touches first, it's just going to assume that was the object it was looking for and drop it into the right bin. Now, let's ramp things up. Let's scale a bit. And one thing to note, like I did say how in a game engine, it can just work out like what the correct objects are, but I'll just go on the record. This is not using that. This is legitimately using the TensorFlow Lite model that got trained in AutoML based on the labeled training data. So this is actually running the TensorFlow Lite model on the Oculus Quest. So just on this self-contained thing on my face, it's running the machine learning model on those images. And you can even see, like, if I move my hand in front of it, it gets a bit confused. It's never seen a hand before. And it'll try to, like, pick up my hand sometimes, yeah. And there we go. That is how we can use AutoML to deploy machine learning to run locally in virtual reality with object detection. I feel like I should have added blockchain to this. That would have completed the circle. But that's everything. And any other points to note? No, this is all doing what it should. Yeah, and the score is eventually going to go positive, and then the manager is going to be very happy. And with that, I thank everyone for listening. And here is a link to the GitHub, which has some of the resources that I talked about in terms of like little code snippets. And I haven't completed the project fully yet, so I'm going to be kind of funneling more resources into this to that GitHub. But yeah, that's it. I'm happy to answer any questions anyone has about the demo or anything else.
Yeah, we're getting a lot of really positive comments in the group chat. But if you head over to the Q&A tab, you have some open questions there.
All right. Cool. So I've got one. Why not use Unreal Engine, which give more power? WRT. So I don't know what WRT means. Oh, I'm not going to try to guess what WRT means with 3D images. So the reason I used Unity is because it was the one I already knew how to use. And it was also when I looked at like, what's the quickest way to build VR with the Oculus Quest? There was loads of examples for Unity. So I chose the path of least resistance by going to Unity because it was a tool I already knew and it was a tool that already had a lot of examples with the Oculus Quest. So that's question one. Next one. How did I implement dynamic window approach in the simulation? I don't know what that is. Dynamic window approach. Did I do that? I don't know if I did that.
Sabam, if you're able to type below in the comments what you mean by the dynamic window approach, that would help. You're also welcome to address another question, Zach, okay, before we get that response.
Cool. Why not use OpenCV to crop wide boxes to tight boxes? Why not use OpenCV? I guess because it was, for me at the time, my experience with using OpenCV is not good. Like just to install it. So I'm not comfortable with OpenCV. And for in the game engine, you kind of saw like, to go from a bounding box with a bit of padding to a bounding box with tight padding, it's like it was literally changing one line to say, instead of use the vertices from the bounding cube, just use the vertices from the object. Like it was a small change for me to get exactly what I wanted. So I guess that's a lot of the answers to the things is just because it was the thing I found easiest to do. So yeah, that was the reason I didn't use OpenCV, is because at the time, like I solved the problem, I believe, a bit easier just doing it in Unity. All right. So I think that's one for the previous talk. Okay, that's one for the previous talk. Okay, this is one. How do we deploy the VR in real world? So this is a great question, because it's kind of like, what is the point? Like, what is the actual point of building this in VR? And there's a couple of points. And one is proof of concepts. It's great because if someone's got an idea and you just want to like get your hands on, usually people are waiting on data sets to come in. You'd be like, you know what? I've already got maybe a pipeline of like generating my own data. So one is proof of concept. So you can prove that, oh yeah, we could solve this problem with machine learning. So one's that. Another one is like, in theory, if say, for example, to actually design those like 3D objects that were being detected, I just bought them from an asset store. I just searched like trash on the Unity asset store and bought them, and they're like assorted bits of garbage. I'm like, I'll just use that for the demo. But if I was like a legitimate like manufacturing company, and I wanted to kind of apply VR and use this to make a real application, what I would need to do to change this is I would just need to replace those objects with realistic renderings of the actual things I wanted to track. And by all means, if I'm a manufacturing company, I probably have those somewhere like in CAD or something. Somebody's probably already got 3D models of our products, and you would take those 3D models, drop them into Unity. And in fact, that's probably where you might want to switch to a different game engine, maybe like Unreal, because I think Unreal, actually, I don't know, but you want to use whatever game engine is going to give you the most realistic sort of images and renderings. And that way, if you train a vision model in a very realistic rendering, in theory, it should just translate to the real world. If you've trained it there and it looks real, when you take that model and apply it to a real world camera, it should also just work in theory, provided you've made sure to not overfit and you give it plenty of examples and made it look as realistic as possible. And also you can also do things like use a lower resolution of a camera to prevent overfitting. So there's all these little things to prevent overfitting, to ensure that when it sees it in the real world, it looks just like in the game. So that's how this would kind of apply to the real world, is making sure the objects look as realistic as they would in your real application. And it should just take that model and apply it to real world. Put a webcam up and it should work. How about using Unreal Engine? Yeah, Unreal Engine, if it's whatever you're comfortable using, all the kind of things I went over in this, there are generic game engine things like cropping out photos and taking a virtual photo from a camera and exporting rig to CSV. They should work. I was just comfortable with Unity at the time. Really awesome. How was the laptop showing the data? It was a video. So I took a screen recording of me using the Google AutoML tool. And in Unity, you can just say, oh, show this video file. And I made like a little sort of event. So if my hand goes near it, it will start playing the video. So that's it. And then at the end, spit out the giant USB stick. Such applications might be useful in AR instead of VR. Yeah, I don't have an AR headset. So for me, it was just accessibility. Like, it was very easy to get my hands on an Oculus. But yeah, absolutely. I'd love to try doing something like this in VR. Have I considered using a Tricondagon as a bounding box? Oh, you may, okay. Okay, yeah, you got me. I hadn't. I think that's all the questions. Is there any more questions? I think that's all the questions.
Yeah, I think going back up to Sabam's comment, that was about the camera inside the laptop. So.
Oh, was it? Okay, all right. Cool.
Perfect. Yeah, thank you so much, Zach. That was honestly one of the most impressive demos I've seen conducted over Zoom.